We can now progress to a quantity that has, on the first view, no obvious connection with the mechanical response of a granular material. This is the contact fabric tensor. This tensorial quantity is defined in this equation, which looks similar to the stress tensor definition. However, only the contact unit normals n superscript c are needed to calculate it, specifically by summing over the dyadic product of n superscript n. The latter is illustrated here in the figure on the lower right. The other quantities are similar as for the stress, and please note that this nc is a dimensionless quantity with a length of unity. The most important quantity that can be derived from the fabric tensor is the coordination number c, i.e. the mean number of contacts per particle. You see the expression relating the trace of the fabric tensor and the coordination number here below. I've also included the definition of the local particle volume fraction here, since it is needed in this relation. As you can see, the definition of phi p and the fabric tensor are quite similar. The former just misses the dyadic product of the contact normals. The final set of metrics of interest I would like to introduce is the deformation or strain. Specifically, one can define a local mean strain as you see in this expression. Note that the last term is the inverse of the fabric tensor, i.e. one must calculate the contact fabric tensor prior to the evaluation of the local mean strain tensor. You may also notice that we here have to calculate the dyadic product of the displacement at contact with the distance LPC already discussed before. As you see, this calculation gives us the full deformation tensor, which is a very detailed information on the deformation of the material. However, it is somewhat unpractical. We will hence not calculate this tensor but restrict ourselves to a global deformation information, which is also what is often done. Therefore, we simply define the following two quantities. The first one is the normal deformation epsilon n, which is simply the ratio of the deformation delta L to the initial length L0. Note that this deformation can be defined, of course, in all three directions of the coordinate system. Second, we define the shear rate, which is the ratio of the velocity upx and the length L0, and has the units of 1/second. Great. We are now done with the pure theory. Let us translate this into practical information on the calculation of stresses and strains in a calculation example. Let us therefore consider a packing of 4 identical particles under the action of gravity. The packing is static, i.e. there is no motion. On the right, I have prepared a sketch for you illustrating the setup. The particles touch in the z direction, which is the wall normal direction, and have an infinitesimal small distance in the x direction. Thus, there is no lateral contact force, but only a contact force in the z direction. Also, we consider a control volume delta V that is located at the bottom left particle. For this particle, we find 2 relevant contacts, the top and the bottom contact. Note the two particles in the right column are not relevant anymore. They will have the exact same stress state as the ones on the left. Let us now calculate the contact forces which are needed to define the stress state. Obviously, these contact forces are different for the top and the bottom contact. For the top, we arrive at 1 particle mass times gravity times the negative z direction vector Ez. We have not indicated the contact force in the sketch. It is simply pointing downwards from the top contact point, of course. Since particles don't move, we can exploit the relation of a force equilibrium in the z direction for this particle here. This unveils that the bottom contact force is 2 times the particle mass times gravity times the positive z direction vector Ez. So this force is acting upwards on the particle. This was already the hard part, and we can now easily evaluate the stress by summing over the contacts. Note the sum over the particles in the RVE degenerates to simply to the contribution of the bottom left particle, because there is no other particle in this control volume. Hence we arrive at this expression here. Continuing our analysis on the next slide, we first simplify the stress expression to arrive at this expression here. We now evaluate the dyadic product, which involves only the unit vectors Ez, to arrive at this simple tensor here. Thus, the stress tensor has only one non-zero entry, which is the ZZ normal stress. As can be seen, the stress is proportional to the product of the particle density, gravity, and the particle size. We note in passing that this ZZ normal stress is identical to the hydrostatic pressure at the center of the bottom particle if we would consider a fluid with a density equal to the bulk density of the granular material. This is since the bulk density is related to the particle density, and the relevant depth for the hydrostatic pressure is 3½ times the particle diameter. We can also evaluate the pressure, arriving at this simple expression here. As can be seen, there are significant normal stress differences for this very special packing. Also, the pressure is only 1/3 of the hydrostatic pressure, which is clearly due to the very special arrangement of the particles. Let us now complete this example with the strain calculation. We consider the example situation as before, i.e. 4 particles loaded under gravity. Next, we have to connect the stress with deformation, i.e. we need to consider a contact force model. Therefore, we assume the simple hook model and fix the stiffness to some known value Kn for both the particle-particle and the particle-wall contact. We can now calculate the overlap at the wall and the overlap of the particles. Adding these two overlaps and considering the definition of the normal strain, we arrive at this expression. Again, we see how the strain is connected to the particle properties, and you see that for a fixed stiffness, the dimensionless strain is proportional to the particle diameter squared. Excellent. This is it for our stress and strain chapter, which should encourage you to perform in-depth analysis of your DEM data.